Now, let me introduce our first speaker, Russell Stakowski from General Electric Hitachi Nuclear Energy. Like I said in Swedish, due to last-minute conflict in schedule, Russell is covering for Patricia Macambi. Russell is joining us from Wilmington, North Carolina, US. And I would like to extend a special thanks to Russell for accepting this last-minute call and also considering it's a very early time in the morning for you over there. Okay, Russell, are you with us? The floor is yours, and please feel free to fill in any information about yourself and your role, which may be relevant for us, for the audience.
Very good. We'll see whether I'm ready. I'm trying to share my screen. Is that working right? And can you hear me currently?
Yes, we can hear you.
Okay, very good. Well, thank you very much for that kind introduction, and I want to thank Patty for giving me the opportunity to make this presentation this early morning here in Wilmington. The magic of technology and working from our own homes means we pretty much can reach out anywhere in the world at any time. So I know I'm very happy to be able to do this and to hear what everybody else has to say regarding developments in nuclear fuel. It's always an interesting topic. Myself, my own background is that I'm Russell Stakowski. I'm the chief consulting engineer for the fuel business here in Wilmington. I'm actually with Global Nuclear Fuel, and I'll get into it in a moment. The relationship between Global Nuclear Fuel and GE Hitachi on the next slide. But as Marcus mentioned, I'm doing this on behalf of Patty Macambi, who is our fuel product manager for the fuel business. What you see there on the right-hand side of this slide is some of the folks that were at a recent outage and pulling out some test rods. Actually, they were working on doing the work it took to get some test rods into our GE 2000 shipping cast for shipment off to Oak Ridge National Lab. So it's an interesting time to be providing this update on technology, since we've been in the middle of technology development at a more furious pace lately than I can remember in our last 40 years. Hard to believe I've been doing this for 40 years, but I looked at my calendar, and sure enough, it's 40 years this year. GE Hitachi is organized around our nuclear strategy, which has four basic pillars. One, of course, is advanced nuclear as reactors. So we have initiatives and programs right now in small modular reactors with our BWR X300. The X, by the way, stands for 10. It's our 10th generation BWR, and 300 is about the megawatts electric that it provides. And also there's the sodium fast reactor program. We actually have two programs now in standing up reactors, both the versatile test reactor to be put in Idaho. We're the lead on that. And the Natrium reactor, which is a joint, can't call it a joint venture, but it's an alliance, and it's a joint contract with TerraPower to stand up a sodium fast reactor that actually produces power and to be licensed under NRC rules here in the U.S. We also have our field services, outages, inspections, plant modifications, and then unfortunately decommissioning services. It's a business, it has to be done. And then plant solutions, various digital and software solutions, the instrumentation and controls and retrofits there and upgrades, and what we call asset enhancement services, which is basically uprating a plant or changing its operating domain, and then a variety of parts and refurbishment services. Then, of course, there's fuel. And in the fuels business is actually where we put global nuclear fuel. So GE Hitachi is a joint venture between GE and Hitachi, and the fuels business is no different. We are also a joint venture of GE and Hitachi. And today we're working on advanced excellent power fuels, and we also have engineering services ranging uranium management in that business. So that's where we fit within the greater GE Hitachi. And where we're located, in case people didn't know, it's kind of a global footprint. Because we're an alliance with Hitachi and GE, we kind of span a few countries here. So the GEH facilities are located in Vallecillos, the nuclear center out in California. We have a test reactor running out there. It runs pretty much every day of the work week. We do radiography services with the neutrons that come out of that. And we have hot cells and whatnot out in Vallecillos. We also in California have a BWR training center, which is quite something to see. It's pretty much a mock-up so that we can go test equipment and go practice things out there before we deploy to the field. We also store fuel in the GEH Morris operation in Illinois. And our headquarters for both GEH and Global Nuclear Fuel is located in Wilmington, North Carolina. Now, with respect to the fuel, and most notably, we have offices in Madrid for GEH and the GENUSA offices there. And the GENUSA fuel factory is located in Salamanca in Spain. But you all probably know that. But I just thought I'd point that out. So we work very closely and have for a number of years that predate the GENUSA joint venture with our GENUSA partners. And then, of course, there's the office in Stockholm, Zurich, and then the Japanese portion of our business is located in Hitachi. And the Rinke works and in Kurihama for the GNFJ fuel facility. All right, for folks, since most of you or many of you are from Vattenfall, you probably already know that we've been supplying fuel there to various Nordic plants for a number of years since the mid-90s with our first reload of GE11, which was a 9x9 product. Total, our experience in the supplying Nordic style fuel has been about 38 reloads or 5,000 bundles, 500,000 rods. And I think we've put fuel in every Swedish BWR, maybe except for the Barsebäck units and OKG 2. But other than that, there's quite a bit of experience with this fuel. Dozens of fuel inspections and excellent crud and corrosion performance. Thank you very much for all the pristine water. That really, really helps. Not our doing, you guys is doing. So thank you for that. And kind of a proven capability for the operating regimes that you have and the strategies. So, to date, our experience is very good. In Sweden, at any rate, the only have debris failures to date. So no PCI. So maybe some of what I'm going to talk about today doesn't have any relevance, but I'm sure you can appreciate it. A large percentage of this fuel has actually operated to its end of life. Sorry for the acronym there. And in the control cells where duty is sometimes seems to be challenging. So moving on, this is sort of taking a step way back and looking at 50 years of operating experience and fleet-wide. And the thrust of technology development in fuel has really been, two-pronged. And one has obviously been in fuel reliability. Now, you guys never had this problem, but primary hydriding in the early 70s with fuel was extreme, and there was just just lots of leaking fuel. So that was a big problem that had to be overcome. And then we ran into successive issues with reliability, like pellet clad interaction and then corrosion issues. By the time we hit the late 80s, maybe, and very early 90s, we had reduced those obvious reliability problems down to things like manufacturing and debris. It was there too, but it was being masked by some of these other issues. The thing about things like reliability is, we've gone through in the nuclear industry times when, fuel failures used to be acceptable. Then we had a change of heart, and we decided that no, we're going to drive to zero. There was a drive to have zero failures by 2010. Zero is a hard number to achieve, but we can get reasonably close. But at the same time, nuclear is fighting for its right to survive. So the fuel also was being looked to provide more economic performance out of the reactor. So what can you do to increase fuel efficiency, to lower the fuel cycle costs? So this is a plot of essentially the defect rate in parts per million, alongside in constant dollars, the fuel cycle savings achieved from product line to product line over the years. And it's kind of stunning that this isn't just us. I mean, this is the whole nuclear industry has been doing this. You need to achieve this performance and alongside the reliability performance. So by systematic identification and elimination of mechanisms, at the same time being able to package that in a form that can offer enhanced economic performance, I think has earned nuclear its rightful place in being able to provide carbon-free electricity. So it's been no small feat to do that. Now, the real trick is, what are we going to do from here on out in order to continue this trend? Because I'm sure everybody wants to see that trend continue. All right, so it does pay to kind of sit back and go, well, how long does it take, and what did you do when you first notice a problem, and what's your response? Well, obviously, necessity. There's an expression in English: necessity is the mother of invention, and that's true here as well. So looking at just the past 20 years, more relevant experience, there's when we had a change in operating strategy in the U.S. It doesn't so much apply in Sweden because you stuck to 1-year operating cycles, but in the U.S. There was a move to go to 2-year operating cycles, which we were able to do. But what that meant was that you wound up controlling fresh fuel. So it was like the second cycle or third cycle of that 2-year operating strategy where we started to notice channel blade interference. Digging into it a little bit, we found that we developed shadow bow on one side of the channel, and that resulted in differential growth and channel blade interference. All right, so then we had to issue monitoring guidance and then start working on what would be a better, more fundamental solution, which is a material problem. So we started developing our NSF channel material, but that takes a long, long time. So it wasn't until 15 years later, basically, that you're able to introduce in mass quantities, a material solution. I'll get to that in a second. And then, of course, silk required a response, also a material solution. But fortunately, this was more in developing the microstructure, so that was a response. PCI failures, when we got the first GE14 ones in 2003 and 2004, was when we finally implemented some fuel operating guides, which treated the fuel a little softer, not quite like the PCI operating guidelines of earlier years, but nonetheless a way of treating it more gently. Obviously, everybody had to learn along with us in terms of how to treat fuel. In 2002, 2005, we have always had, a debris filter in G14, but we started seeing a lot of fuel failures in certain plants, in particular Brunswick, which was a wake-up call that even if you have a filter, you can still overcome it. And so we started a development program and implemented our non-line of sight lower tie plate debris filter, and also went to the source of the problem and implemented feed water debris strainers in the recirculation system, particularly with pump forward drain plants. Sometime around 2007 or 8, actually, we kind of ran into what we call high residence time failures, and this is where you have relatively low power density plants, and they're able to have the fuel in there for quite a while, and they had a duty-related failure, and it appears to be related to residence time, and the morphology of how that actually fails is still being debated, but we think we know how to diagnose when that might happen. And then, of course, 2015, we got some failures even in our Defender lower tie plate, and so we look to improve its performance. And then, even today, we are having some debris failures out in the industry. And so we're looking at even a next generation debris filter and looking for making cladding a little more robust. So where do we go on this fuel reliability? Well, we continue our defense in depth. There are a number of things I just listed which were pretty effective at controlling debris. We just haven't been able to stamp it out. So we kind of categorize it into four different categories. One, don't let the debris get into the reactor. So if it's there, get it out. If it does get into the reactor, don't let it get to the fuel rod. That's where debris filters come in. And if it does get to that fuel rod, don't let it trapped in that spacer next to the fuel rod. And if it does get trapped, don't let it fret through the rod. So those are the kind of four things we have been looking at. All right, so debris prevention. The industry has done really well. There were some plants that had intrusions of debris from various plant modifications, and then maybe some poor practices, and they have really stepped up to change the way that they handle foreign material and exclude it from the reactor. We've changed manufacturing practices to make sure that when we ship a fuel assembly, that's all you get is the fuel assembly without any foreign material hiding out in the boxes. Outage services, I mentioned that GEH performs a lot of outage services, and so very high on the list of things they practice is making sure that they have techniques and procedures that minimize the chance for introducing additional debris into the plant. Some plants have done high efficiency ultrasonic cleaning of the fuel. This is ostensibly done for control of crud, but in fact, we're not too sure that it does a lot for dose. Which is what they were going after. But it's certainly, when you clean the fuel, whatever debris is there tends to come out in that cleaning as well. So while you're kind of shaking exposed fuel, it nonetheless is good for removing debris. Fuel is a very good debris filter itself. It certainly catches whatever debris gets into it. So if you clean it, that's certainly one way to remove it. And people are also taking very aggressive actions to identify the sources. Recently, we've had a number of cases, at least in the U.S., where there's a vari-seal and in a valve, and that has come apart, gets chopped up by the pumps, and becomes fine enough debris to enter the fuel. And we've seen that after the fuel was cleaned, we can identify which seal that came from in the plant. And so cleaning up spent fuel pools also to remove kind of legacy debris is also proven an effective means. Right. It did mention that we're doing a debris filter modification. We're looking at the next generation debris filter. Our current one is called Defender. It's a non-line of sight filter. Defender Plus was a modification of that one incrementally to try to improve its effectiveness. And what you see here is a debris size versus that of filter effectiveness. And everybody's chasing this. We're not the only ones. Try to eliminate the smallest debris that you can out of there. You can't eliminate everything because then you have no water flow. So you got to leave some room for water. There's no question about that. And so we're trying to do that. What we did, in fact, for the next generation filter is we had a contest a number of years back. We said, hey, with additive manufacturing, you can make devices that you couldn't even imagine creating by some traditional means. So we had some dozen or 24 types of debris filters designed. They said if you could draw it, you could build it. But you weren't restricted to something that was traditional. So we had some of the designs. I don't know whether you guys are familiar with Mortis Escher. There's a statue or I guess a sculpture called Gravitation, and it's basically a stellated dodecahedron, and it's got all these crazy points on it, and you look at it and you go, only Escher could draw that. We had a debris filter that looked like that. We created those with additive manufacturing, and we went head to head with the designs, and we chose the best out of those in terms of effectiveness, and we ran with that for pursuing our next generation debris filter. And it turns out that was a good exercise, because it looks like we're getting capabilities at 2 to 3 times effectiveness in the smallest of the debris. Now, the smallest of the debris, what we're showing in this picture here is, I'm really trying to show you debris getting caught in the spacer that we don't like. But this little there we go. This wire here is where probably the mid-range of the debris we're chasing. But it got caught on our V-notches. The V-notches were there simply for manufacturing, but as it turns out, these are really good at catching debris. So our later spacers, in fact, do not have those V-notches. We took those V-notches, in fact, and put them elsewhere in the Defender filter, because they're so effective at catching debris. So working on the spacer, making sure that there's clearance where there's stops and springs, so that the debris flows on through rather than getting caught. All right, and then there's a couple of things we're doing for debris prevention when it does get caught. So if it does get caught under the spacer, as you see the evidence of it on the left-hand side here, it can easily wear through. So what we had been working on for a long time, because you can minimize that sort of thing, but you can't eliminate it. As long as there's something getting close to the rod called a spacer, you have the potential that it can in fact get caught there. Can't eliminate it entirely. So what you can do is you can make a fuel rod, perhaps, that is resistant to that. So we had been working on a coating which was abrasion resistant. And when we put it through its paces of can it withstand the BWR environment, we noticed that its corrosion performance was also extraordinarily good. And so it became more oxidation resistant. So we nicknamed it ARMOR, which is the acronym for abrasion resistant, more oxidation resistant. And so it resists fretting better than the Zirc and the natural Zirc oxide that forms on fuel rods. It's a very thin layer overlaid on top of our Zircaloy. Today we are the story about the spacers. So if you're just looking for abrasion resistance, you really only have to worry about putting it under the spacers because that's where debris gets caught. However, because of its superior performance in oxidation resistance, we went, well, wait a minute, corrosion resistance is a great thing. We really need to coat the whole rod. And so we've been working on our coating machines to be able to coat the entire fuel rod. And so what you see on the right-hand side is the rendering of what that machine that is going to be installed in Wilmington will look like. There we go. There's a handful of other technologies that we've developed and are ready for harvesting, if you will, to help various reliability issues. One, of course, is we've been working on additive, and we have the furnaces able to do that. We have NRC approval to use the additive in the fuel pellets, and there's operational experience to extended burn-ups. So when the time is right for including that for PCI resistance, we are able to do so. We also have Xyron cladding, which has improved corrosion and hydrogen pickup performance. We got approval from NRC more or less recently for that because we had to do that because it was outside the ASTM range. But we have that available as a solution as well. And then I kind of mentioned our NSF, which is a niobium tin iron zirconium alloy for channel interference. It's got improved fluence and shadow bow resistance versus the zircaloys, and is essentially equivalent to zircaloy channel in terms of dimensions and mechanical performance. And it's proven itself to be quite an effective remedy for this control to channel distortion that we're interference due to the channel distortion. We began in 2000 and got approval 15 years later. We now have like 12,000 channels with operating experience, and to the right you see why we like it so much. This is a measure of bow. In mils, sorry about the units, I couldn't change that, but 100 mils is about 2.5 millimeters. The black dots here is the scatter of the data of what the measured bow is. It's just got lots of variability. And the NSF are the yellow and red. It's got a much tighter performance. And so even if you don't have an issue with channel to control blade interference due to this bow mechanism, nonetheless NSF is got this tighter performance, and that can always be harvested for design reasons. And when you get these charts, you'll see that it's in inch days is a measure of how much control in the early life there was. If you think English units are bizarre, these inch days are even more bizarre, but it's essentially a measure of how much control there was early in life. All right, so that dealt with reliability, and how we do that is we introduce the technology as we can with the next product line. So as the technology matures, gets approved by the various regulatory authorities, we go ahead and introduce that. I won't bore you too much with the walk of our product lines from the early days, but since the 90s, we've been on our 10x10 fuel generation, and really that has been a question of being able to increase fuel efficiency, usually through linear heat generation rate improvements, and also adding, for us, adding mass. The early 90s saw quite a number of power up rates, and there was a demand that there just simply be more fuel in the fuel assembly. And so we did that by going to GNF2. GNF2 put several kilograms more of actual heavy metal into the fuel assembly. We improved the critical power performance, and we also improved its linear heat generation rate simultaneously. And of course, that has the net effect of increasing the fuel cycle benefits that you get from operating that fuel with lower batch fractions. Going to GNF 2.02 was mainly about getting some additional reliability and features in there, including the spacer improvements and the Defender Plus. And we also took a look at the software or technique of how you manage critical power. And so we offered an upgrade to that treatment. And so that's what we've got in GNF, what we call 2.02, available worldwide and also here in the Nordics. And that's, we have the appendage N when we are able to offer that in the Nordic style. All right, those are all more or less incremental improvements. And there's a story here about ATF. ATF is accident tolerant fuel. And to a large degree, when this started, DOE had said, you know, what can we do to help the industry? And we came up with some great ideas. All three fuel vendors came to them with some interesting ideas they wanted to pursue. And the kickoff meeting for that program, which was in the Advanced Fuel Cycle Initiative, happened on March 15th, 2011. 4 days after the Great Tohoku earthquake and tsunami. So that was a very somber day for the industry, and what had started out being an interest in really changing the way fuel was conceived of in the industry, it became, what can we do to prevent consequences of an accident? And so there were a number of years spent chasing exactly what that would look like. And then, you know, the utilities were a little bit lukewarm as to whether that would really manifest itself in something that would be useful to them, where they could probably get the same types of accident response improvements in other ways. But when we started looking at the different components of what goes into the accident tolerant fuel program, you know, you can harvest some of this technology really to improve the overall economics of the entire fuel cycle. And so that really sparked the interest of the industry, and it's been going really quite swimmingly well, you know, ever since that time. And so what we have in our accident tolerant fuel program arrangements with the Department of Energy, we brought in our armor technology into that and said, hey, you know, if this is so good at corrosion performance, you know, why don't we make it part of it? And they absolutely said, you know, agreed to that. Other components of that are higher enrichment, what we call low enrichment uranium plus, and that's the enrichments between 5 and 10%. You really need that if you're going to couple it with high burnup, and this is where the industry, the red dotted line is where the industry really finds you know, attractive fuel cycle economics, is if they can achieve these things together. To go to high burnup, you typically need a little bit more enrichment, so we need to go over 5%. We were also looking at other cladding technologies. So our ironclad technology is a iron chrome aluminum alloy that shows great performance in steady state and accident performance. And then we also were looking at channels being ceramic matrix composite, and eliminating more zirc out of the core, thereby improving hopefully neutron economy as well as accident performance without having that zircaloy in the reactor. And then, of course, looking at taking a big swing, looking at different types of ceramics for the actual fuel material itself. So I've already kind of talked about armor quite a bit, but you know, we had already installed test rods in 2008. We've harvested them last year and have moved those over to Oak Ridge National Labs for the post-radiation examination to start. And that's kind of underway. Coupled with armor, again, because of its performance with corrosion, we also believe that we can extract some thermal limits benefits out of doing that. Now, for LEU Plus, that's quite a switch. That's a major bit of work, and that requires a modification to our factory license. A lot of the criticality safety analysis, that's CSA, and our integrated analysis, that's currently underway. And we're making ready the factory in order to go to those higher enrichments, and working with the industry to define exactly how we will take advantage of that increased enrichment. And licensing our methods to be allowed to go up to those kind of enrichment levels. And we're targeting currently that the first reload of high enrichment will happen in 3 years from now. High burnup, down through my career, we've always said high burnup, and it's always been the next step in burnup. But in this case, we're talking about 10 and 20% higher than where we are today. We've had high exposure experience in Europe, down in Germany, Switzerland, and we're engaged in the Studsvik programs. And also, I believe, Studsvik is an important element of extracting data from some of that high exposure experience in order to make it relevant to the rest of the industry. And we have our licensing regime that we do in the U.S. And we've been allowed to take lead test assemblies up to higher exposures, and we've got some more of that planned in the near future here. And we're also looking at risk-informed and performance-based licensing, which is very different than the prescriptive type of licensing regime we have in the U.S. And we're seeing what that means in the very near future here. As I mentioned, Ironclad is we've got test rods of that, and they've come out, and we'll be looking at those shortly. And we've got our programs in channels and composites still moving. Let me move on. I'm sorry taking up all your time. I would be crazy if I didn't say kudos to the Department of Energy. This is work done under a program, and here the information is given here. My views don't reflect those of the U.S. DOE, but I thank them anyway. All right. I'll kind of skip over this very briefly, but this you'll have in the package when you get it. But when I say LEU plus affects the entire fuel cycle, I mean everything, except for maybe the mining. But everything from enrichment and transport of the raw material, how you get it to our factory, how we get it around the world in shipping containers, the basis of our criticality methods for the fuel factory, and just the waste streams in the fuel factory and the sizing of componentry, all of that needs to change. In addition to the stuff in the reactor, which is what I talked about, you also have to worry about the fresh fuel shipping container and the fuel storage at the site, the methods and fuel performance, as well as when you discharge. There's assumptions that have been made about what's been discharged, and when you go to high enrichment and high burnup, all of those assumptions change. So while it sounds easy enough to say, yeah, we're going to go to high burnup and high enrichment, all of these things need to be changed all at once before you can load the first one. And then I mentioned risk-informed and performance-based. This is something that the U.S. NRC has been talking about for a while. Right now, what we're hearing from them is that they really are trying to innovate. You guys don't have to put up with this necessarily. We've been very, very prescriptive in the U.S. We have these regulation guides that if you don't adhere to them, well, you have to prove, the burden of proof is just really large to be able to overcome that sort of thing. And NRC has decided, and under their instructions, that they really need to take a look at, is this truly important to go chase? Is this really a risk? And is it based in actual performance, or am I holding you to just a process? And in this way, NRC is maybe moving a little more towards how SSM has always traditionally been, where they've put some thought into whether it's really an issue that's pertinent to safety or not. And so we're exploring this with them. NRC is happy to be working with us, and we're happy to have that conversation. Us and a couple of utilities in the U.S. are kind of spearheading what this means for fuel licensing. So we'll keep you updated on how that goes. I hold out great hope that this can yield benefits for everybody. All right, and finally, when we take a look at all of those things that we've been developing, we imagine our product strategy to be one that continues to harvest the technology as it comes along. In the U.S. and elsewhere, we've got GNF3 is going to be deployed. That's been through its U.S. licensing. It was meant to take yet another step in terms of improved fuel cycle economy by adding, additional length of rod for LHGR and additional mass in the bundle, so that the energy performance of that bundle is greater. And to do so, we've kind of harvested some of those techniques we derived, put it into the bundle, and made our justifications. And so the entire envelope is one of both increased efficiency, higher mass, improved critical power performance through hardware, and a little bit in how we did our correlation for critical power. So we were able to improve the way we did our software there, and I think it's shown great benefit. When we get to later in the 2000s, some of that ATF technology being derived, that technology will be put into a fuel assembly called GNF4. We're not completely certain which ones we're going to put in there, but obviously we're going for yet increased fuel reliability, and likely harvesting the things we do to be able to go to high burnup, as well as high enrichment, optimize it a little better. And of course, with that, increased efficiency, lower fuel cycle costs, as always, and some margin for longer cycles. We also anticipate that the accident tolerant part, where you're looking at corrosion performance and maybe hydrogen pickup improvements, that we'll be able to harvest that for potential for LOCA event relaxation and take advantage of those margins and get fuel economy out of that. And also there will be a reimagining of how we do critical power limits. We looked in the 90s, we looked at time at temperature, in fact, in Sweden. And so we look forward to doing something akin to that. And then, of course, there's the GNF Next, which will have something to do with lattice harmonization. And again, we might harvest ironclad for that one and other exotic materials. All of this is kind of being underpinned by the fact that we've got BWRX, which is a BWR, and it uses the standard GNF2 bundle. So we really see BWRX as kind of a future BWR that'll be being put in place for the 2030s and 2040s and beyond. So it's really sustaining this technology development of ours and in the BWR fuel fleet. So we look forward to a great future for BWR fuel, more technology development and continued presence in Sweden, and BWRX, hopefully Estonia and Poland, which we're working with as well, and so continue that BWR presence in Europe. So, anyway, with that, I'm done. I'm sorry I took so much time, Uffe.
Okay, thank you very much, Russell. There's an echo here. But okay, so we have some time for some short questions. We have some in the chat, and let me bring them up. First one is regarding debris size. You talked about small, smaller, and smallest debris. What do you mean by that? Which form and how many?
Okay, so the debris size is characterized by it's difficult because there is both a diameter and a length involved. And so what we're talking about is fractions of a millimeter in diameter and a few, I don't know, somewhere between 4 and 10 millimeters in length, maybe even 3. So something like that is the smallest debris. If you get much smaller than that, it kind of becomes not of consequence because it really doesn't have the ability to vibrate if it does get caught. There is a debris size. We don't know precisely what it is, which is small enough to not be of concern. And so the smallest debris we're chasing is that millimeter size in length, several, and sub-millimeter in diameter.
Okay, thank you for that explanation. Next question was regarding fuel rate. What is the maximum allowable fuel failure rate, primary or secondary, provided that the system is perfect?
If I understand the question, it's to me that's certainly one for a utility, our utility friends to answer. What's the allowable fuel rate? I would say 0, right? We are certainly trying to have 0 fuel failures. It just because one fuel failure, it depends on where you are, but one fuel failure, if it goes wrong, it can cost a utility $10 million. That's just a lot of money for one single failure because they have to shut down, take it out, if they can't operate. Now, obviously, we have failed fuel management techniques that we've deployed. We assist plants with that. Everybody has kind of a different way of handling that, but you can operate for 2 years with failed fuel. So it is acceptable to do so, but nobody likes to do it. So we're trying our best to have no fuel failures.
Thank you for that addition. Now, okay, there is one technical detailed question here. It's regarding thermal expansion. How will the thermal expansion of the cladding and the displacement per atoms impact the coating degradation?
Yeah. And this is why we do testing to make sure we understand that. Now, thermal expansion, of course, can be tested, and depending upon the type of bond you have, it will do different things. So the material and the type of bond are going to determine how much thermal expansion and, in fact, contraction, right? Because when a fuel rod, first operates, the first thing it does is it grows axially and cinches down, and then there's going to be kind of a swelling as the pellet collides with the cladding and pushes it out. So the coating has to survive all of that. Now the coatings are also very thin, and so the amount of damage they receive total isn't very high. Now it's there and it transmutes, but it transmutes just like zircaloy and oxygen does, in the zirc oxide layers. So the coatings need to be able to survive both those. Yeah, just.
Okay, I had some questions myself, but I think perhaps we can wait with. Will you stick around with us until the end, or do you have to?
Yes, I will. No,
okay.
I can stick around.
Oh, thank you very much, Russell. But because I think we move on now to Uffe.
Yeah,
although
I wouldn't miss his presentation, so I'm going to be here.
Right. Okay, so move on to our next speaker.